Today we're going to talk about the chain rule. So let's recall something from our algebra days. If you recall the composite function, f composed with g of x, that means into the f function you're going to put the entire g function. So for example, if we had f of x was 3 minus 2x squared and g of x was 7x minus 5, if we wanted to do f composed with g of x, that means we would do f of g of x. So into f, we will put the entire g function. Well, as you can see, g of x is 7x minus 5, so into f, we're going to put 7x minus 5. What does f do? F is 3 minus 2 times your input squared. So we'll do 3 minus 2 times 7x minus 5 squared. Here we'll have to distribute this out, 7x minus 5 times 7x minus 5. So I'll do that distribution that you call FOIL. Everybody in the first group gets multiplied to everybody in the second group. And so now I can distribute my negative 2 to everybody in there, combine all of my like terms, and I see that f composed with g of x is negative 98x squared plus 140x minus 47. Now what if we switch that? What if instead of doing f composed with g of x, we did g composed with f of x? So into g, I'm going to stick the entire f function. So this is going to be g at f of x. Well, remember that f of x was 3 minus 2x squared. So into g, I'm going to put that entire 3 minus 2x squared. So what does g do? G does 7 times your input minus 5. So 7 times that 3 minus 2x squared minus 5. Distribute our 7, combine like terms, and we get that g composed with f of x was negative 14x squared plus 16. Now, note that f of composed with g of x and g composed with f of x are two completely different operations. They are not commutative. You can't. F composed with g is different than g composed with f. So now let's bring up the chain rule. So again, if f of x and g of x are differentiable functions, we've seen this before, then the derivative of f of g of x, or f composed with g of x, would be the derivative of f evaluated at g of x times the derivative of g of x. So you would take the derivative of this outside function f of x, leave that inside function alone, and then tack on the derivative of that inside function. Another way we could look at it is that if y was a function of u and u was g of x, so if y was f and we call this u, if we call g of x u, then the derivative of y with respect to x would be the derivative of y with respect to u times the derivative of u with respect to x. So I'll start by using this to help you a little bit here. Let's take a look at our first example. Find the derivative of x cubed plus 2 all raised to the 50th power. So looking back here, this is going to be my outside function, and this is going to be my inside function. And the more that you practice, the more you'll be able to determine what your outside and what your inside functions are. So looking here, looks like this x cubed plus 2 is my inside function, and this inside function is all being raised to the 50th power. So I'll call my inside function that x cubed plus 2. So then the derivative of u with respect to x would be 3x squared. And then my outside function, which is a function of u, I called this u. So my outside function would be u to the 50th. And then the derivative of y, that outside function with respect to u, would be 50u to the 49th, just using the power rule. So now the derivative of y with respect to x, as we said earlier, would be the derivative of y with respect to u, right here, times the derivative of u with respect to x, right here. So I'll substitute those in. Now the problem with this is, and I can simplify this, right? I can do 50 times 3x squared to get 150x squared times u to the 49th. The problem with this is that my derivative now has a u in it, and I'm trying to differentiate y with respect to x. So I shouldn't have a u. This whole thing should be in terms of x. But what is u? We said u was x cubed plus 2, so we can substitute that back in. So the derivative of x cubed plus 2 all to the 50th power is 150x squared times x cubed plus 2 all to the 49th power. Let's look at another example. Let's find the derivative of y equals the square root of x squared plus 5x. Now, as discussed many times, we don't have derivative rules for radicals, so we're going to have to get rid of that radical and write it as a fraction exponent. So instead of the square root of x squared plus 5x, it'll be x squared plus 5x all to the 1/2 power. So now I have an inside function, x squared plus 5x, and an outside function, this whole thing is being raised to the 1/2 power. So I can call u my inside function, x squared plus 5x, and then I can find the derivative of u with respect to x using my 4 basic derivative rules, 2x plus 5. And now my outside function would took this inside function u and raised it to the 1/2. Then I can find the derivative dy du, the derivative of my outside function, using the power rule, 1/2 u to the negative 1/2. We can get rid of that negative exponent and put it back in radical form, and we get 1 over 2 times the square root of u. So now the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. Well, dy du we've got right here, and du dx we've got right here. But again, we pose another little bit of an issue here, where we have the derivative in terms of u, but we're trying to take the derivative with respect to x. Good thing is we know that u is x squared plus 5x. So when I simplify this together, I can bring this 2x plus 5 up top, replace what my u is, and the derivative of the square root of x squared plus 5x is 2x plus 5 all over 2 times the square root of x squared plus 5x. So let's look at some more examples of the chain rule. What if I wanted to find the second derivative of f of x equals 2x plus 9 all to the 10th? Now, at some point, I want you to get familiar enough with the chain rule where you don't have to actually call out what u and du dx is and what y and dy du is. We can just say, hey, right here's the inside function, and the outside function is taking this inside function and raising it to the 10th power. So very soon, I want you to get to the point where you realize, hey, this is just sort of an application of the power rule, where I'll bring the 10 down, leave my inside function alone and take 1 away, and then I'll tack on the derivative of that inside function. So bring the 10 down, leave the 2x plus 11 alone, take 1 away to make a new exponent of 9, and then just multiply it to that derivative of that inside function, 2x plus 11, which would be 2. And now we can simplify this. 10 times 2 gives me 20 times 2x plus 11 to the 9th. So that's the first derivative, but I'm trying to find the second derivative. So when I go to find the derivative again, this 20 is now a coefficient. It's just going to multiply in at the end. And here is another application of my chain rule. I have my inside function being raised to a power. I can bring that power down, leave the inside function alone and take 1 away, then multiply it to the derivative of that inside function. So the 20 is the coefficient. We brought the 9 down, left the 2x plus 11 alone, took 1 away for our new exponent, and then multiplied by the derivative of that inside function. And then that 20 times 9 times 2 will simplify to 360 times 2x plus 11 all to the 8th. So we found the second derivative. Let's differentiate g of x, which is 3x squared plus 2x all to the 4th, times x cubed minus 9x all to the 5th. Now notice in here we have variable times variable, which means we're going to need to use the product rule. Derivative of the first times the second, plus the derivative of the second times the first. But when we go to take the derivative of the first and we go to take the derivative of the second, then we're going to have to apply that chain rule. So if you remember, we said that the product rule here would be the derivative of the first times the second plus the derivative of the second times the first. So we're going to let u be this first thing, 3x squared plus 2x all to the 4th. Now when I go to find u prime, I will have to use my chain rule, bring the 4 down, leave the inside function alone, take 1 away, and then multiply by the derivative of that inside function, which we can simplify, right? We can't distribute the 4 in here because exponents come before multiplication, but we can distribute the 4 to the 6x plus 2. And so now our u prime is 24x plus 8 all times 3x squared plus 2x to the third power. And then our v will be the second term right here, x cubed minus 9 all to the fifth power. Now when I go to find v prime, again I'll have to use the chain rule. Bring the 5 down, leave the inside function alone, take 1 away, then multiply it to the derivative of that inside function. And again, exponents come before multiplication, so I can't distribute the 5 here, but I can distribute the 5 to the 3x squared to get 15x squared. So now using my product rule, u prime times v plus v prime times u, I've got u prime, I've got v, plus I've got v prime, and I've got u. To get this big long derivative here, 24x plus 8 times 3x squared plus 2x to the third times x cubed minus 9 to the fifth plus 15x squared times x cubed minus 9 to the fourth times 3x squared plus 2x all to the fourth power. It's a big long derivative. I don't expect you to simplify that any further and distribute anything out. Let's take a look at one more example. Let's find the derivative of the cube root of x minus 1 over 2x plus 3. Now notice here again, we don't have a rule for radicals, so we're going to have to rewrite that as a fraction exponent, all of that being raised to the 1/3 power. So now I have an inside function being raised to a power. What I'll do is I'll bring the power down, leave the inside function alone, take one away, but then I'll have to multiply it to the derivative of this inside function. But when I go to take the derivative of that inside function, I have variable over variable, I'm going to have to use my quotient rule. So again, bring the 1/3 down, leave the inside function alone, take one away, and then times the derivative of that inside function will be the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom square. Now this right here is something that's easy to simplify. Distribute the 1, doesn't change anything. Distribute the -2, and then I can combine my like terms to see I have 1/3 times x minus 1 over 2x plus 3 all to the -2/3 power times 5 over 2x plus 3 squared. This is a perfectly acceptable answer, but we can simplify this further if we needed to. So let's simplify that answer. This is the answer we got, 1/3 x minus 1 times 2 over 2x plus 3 all to the -2/3 over 5 times 2x plus 3 squared. Now, what we can do here is we can actually distribute this exponent and take the x minus 1 to the -2/3 and the 2x plus 3 to the -2/3. To get rid of a negative exponent, you move it to the opposite side of the fraction bar, so we'll bring this down to the denominator and we'll bring this up to the numerator. And now if I was going to multiply all of this together, multiply all my numerators, multiply all my denominators, I get something like this. But notice 2x plus 3 to the 2/3 and 2x plus 3 to the second, these are the same bases. Like bases being divided, we can subtract their exponents. And 2/3 minus 2 will give me -4/3, which I can bring down to the denominator to make it positive. So really the nice simplified answer here for that big derivative would be 5 over 3 times x minus 1 all to the 2/3 times 2x plus 3 to the 4/3. So that's an introduction to the chain rule. As you'll see when we get into bigger functions like your exponential functions, your logarithmic functions, and your trigonometric functions, the chain rule will play a very important role. That's it for now.